RMS voltage. 5 infinite impedance voltmeters calibrated to read root mean square values are connected as shown in the figure. So we have voltmeter 1, 2, 3, 4, and 5. Let the resistance R be 200 ohms, inductance be 0.4 henries, and capacitance 6 microfarads, and the voltage V supplied by this AC source is 30 volts. What is the reading of each voltmeter if omega, the angular frequency, is 200 radians per second? Now, if I concentrate on the voltage reading that I will see on the resistor V1, this will be due to the RMS current that flows through the resistor multiplied by the resistance. So I can write V1, the RMS value of the voltage read on the resistor V1, is the RMS value of the current multiplied by the resistance. Now, if I do the same thing for V2, this will be the inductive reactance of the inductor multiplied by the RMS value of the current. So that would be V2 reading. So I can see that V2 will be equal to IRMS times XL. Now, doing the same thing for the capacitor, I will have V3 equals IRMS times capacitive reactance XC. So that is the voltage across the capacitor, capacitive reactance times IRMS. Now, when I look at V4, I have two circuit elements connected in series, the inductor and the capacitor. The inductor has a 90-degree phase with respect to the current, positive 90 degrees, the capacitance negative 90 degrees. So it will be V4 times, V4 will be equal to IRMS times XL minus XC. That's the effective impedance of this part of the circuit. So I can write the voltage reading on the 4th voltmeter is IRMS times XL minus XC. And for the overall circuit, I have three circuit elements connected in series. The impedance Z will be square root XL minus XC square plus R square, so multiplied with the RMS current, will give me the reading on V5. So you can see it's reading the voltage across the three circuit elements R, L, and C. And R has a current, the impedance of the resistor is R, which is basically which is going to have no phase difference with respect to current. And then this inductor will have XL with 90-degree phase difference and XC with minus 90-degree phase difference. So that we have this impedance square root XL minus XC square plus R square, impedance multiplied by RMS current, will give me the voltage reading. So here IRMS, the RMS current, is the voltage supplied by the AC source RMS value divided by the impedance of the circuit. And I have inductive reactance equals to omega times L. The capacitive reactance equals to 1 over omega C. And the resistive reactance is equal to R, that is independent of the angular frequency of the source. So looking at this more carefully, on this phasor diagram here, I have XL making a 90-degree angle with respect to the current. So this is the plus 90 degree. And for the capacitor here, I will have a minus 90 degrees angle with respect to the current, and for the resistor it's in phase. So we can see that the impedance will be XL minus XC on the positive direction, and then we have resistance R on the x-axis, so this is on the y-axis. The impedance Z will be making an angle phi with respect to the resistance, and it's going to have a value, an amplitude, which is square root of XL minus XC squared plus R squared, because it's the hypotenuse of this right triangle. Okay. Now, what is VRMS? The RMS value of the AC source. It is the amplitude of the voltage, AC voltage, V divided by square root 2. And what is the RMS current then? The RMS current will be equal to the RMS voltage, V over square root 2, divided by the impedance of the circuit, XL, which is omega L, minus XC, 1 over omega C, parentheses squared, plus R squared, square root. Okay, so this will give us IRMS is equal to V multiplied by omega C divided by 2 omega square LC minus 1 squared plus 2 omega RC squared inside the square root. Okay, so here we multiply the top with omega C, omega square LC divided by omega C minus 1 over omega C parentheses squared, and this is also multiplied and divided by omega squared C squared, and you have 1 over omega C squared at the bottom inside the square root, so that goes on top as omega C, and square root 2 goes to the bottom, so 2 parentheses omega square LC minus 1 squared, and plus 2, we have 2 omega RC squared. Now we can substitute this for the RMS current value in order to find V1 reading. The V1 reading is the RMS current multiplied by the reactive resistive reactance, which is V now R omega C divided by 2 omega square LC minus 1 squared plus 2 omega RC squared square root. And then for V2 reading, we have the inductor, so it's going to be multiplied by omega L this time. IRMS will be multiplied by omega L this time. So it is V omega square LC divided by 2 omega square LC minus 1 squared plus 2 omega RC parentheses squared inside the square root. That's V2 RMS value. For V3, we have the voltage across the capacitor. Now this is going to be multiplied by 1 over omega C. So in the RMS current, I had V omega C multiplied by 1 over omega C. I'm left with V here. 2 omega square LC minus 1 squared plus 2 omega RC parentheses squared inside the square root. That's V3 reading. V4 will read the voltage across the inductor plus the capacitor. So that is multiplied by XL minus XC. So if I multiply V omega C with omega L, I will get V omega square LC, and then minus 1 over omega C, it will give me a minus 1 here, divided by 2 omega square LC minus 1 squared plus 2 omega RC parentheses squared, square root, that's for the V4 reading. And now I'm left with V5 reading, which is the voltage that appears between the terminals A and B. That's actually going to read the source voltage here, but in terms of the RMS current, we can write this as V omega C multiplied by omega L minus 1 over omega C squared plus R squared, square root, divided by 2 omega square LC minus 1 squared plus 2 omega RC squared inside the square root. But as I said, it will just be a reading of V. And let's put these into the box here. So our V1 reading will be VR omega C divided by square root 2 omega square LC minus 1 squared plus 2 omega RC parentheses squared. For V2, the top will be V omega square LC. For V3, the top will be V. For V4, it will be V times omega square LC minus 1. And for V5, it's just going to be V, but it can also be written this way. And now I have the values of the voltage, amplitude, the resistance, inductance, and capacitance here. So I have these values, and I'm also given that omega is 200 radians per second. And from this, I need to calculate the numerical values for XL, XC, XR, etc. To find the final results here. So this will be XL, which is omega L, that is 200 radians per second times 0.4 henries. This will give me 80 ohms for XL. For XC, I have 1 over omega C, 1 over omega C, that is 1 over 200 radians per second times 6 microfarads, 6 times 10 to minus 6, that is 833 ohms. For the impedance of the circuit Z, I have square root XL minus XC squared plus R squared. This is all inside the square root. So this will give me 80 minus 833 square plus 200 ohms squared, which is 4 10 to 4 inside the square root. So the impedance of the circuit is 779 ohms. Now for the RMS current is the amplitude of the voltage divided by square root 2 divided by Z. So this gives me RMS current value 30 volts divided by square root 2 divided by 779, which is 0.0272 amperes. Now I'm ready to calculate V1, V2, V3, V4, and V5. So let's do that here. V1 is IRMS multiplied by the resistance. So that is 0.0272 amperes multiplied by 200 ohms. So that gives me a V1 value of 5.44 volts, the RMS reading. For V2, I have IRMS times XL, which is 0.0272 multiplied with 80 ohms. So that gives me V2 reading to be 2.18 volts RMS. V3 is IRMS times XC, which is 0.0272 amperes times 833 ohms. So that gives me for V3 22.7 volts. V4, the voltage across the inductor plus the capacitor, I have IRMS multiplied by XL minus XC. So that is 0.0272 multiplied by 80 minus 833 absolute value. This gives me a V4 reading of 20.5 volts. And as for the V5 reading, I can do it two ways. I can say V5 is just the input voltage V divided by square root 2, or I can say it's equal to IRMS times Z, which is 0.0272 multiplied by 779 ohms, which is V5 value 21.2 volts. Okay, so as a summary, we have V1 5.44 volts, V2 RMS 2.18 volts, V3 22.7 volts, V4 20.5 volts, and V5 21.2 volts. Okay, so in this problem we looked at an RLC circuit. The resistance, inductor, and the capacitor were connected in series. We looked at the voltage across the resistor RMS value, voltage across the inductor RMS value, voltage across the capacitor RMS value, voltage across the inductor plus the capacitor RMS value, and voltage, that's the supply voltage RMS value, or voltage across RLC. For each circuit element, I have to determine the reactance. The reactance of resistance is R, inductance is omega L, capacitor is 1 over omega C. And for the combination of inductor and capacitor, the impedance will be, without this R part here, XL minus XC. Including the R part, the impedance of the circuit can be found, which has a magnitude square root of XL minus XC square plus R square. That is because the voltage across the inductor leads the current by 90 degrees, but voltage across the capacitor lags the current by 90 degrees. So that comes from this phasor diagram. And with that, I can calculate the RMS current as VRMS divided by the impedance of the circuit and multiply that RMS current with the circuit element reactance R, XL, XC, or combination of inductor and capacitor XL minus XC, or for the overall circuit with the impedance Z, or I can take the amplitude of the input voltage divided by square root 2 to get the RMS voltage reading for the source, and that gives me my list of final answers for V1, V2, V3, and V4 and V5.